And it's my pleasure to share our work here. The paper title is From Full Data to Few, DQN-Driven SV Data Selection for One-Class SVM Anomaly Detection. Here is the outline of my presentation. It will be divided into 4 parts. The background and the motivation will be mentioned in introduction parts. For the methodology part, we will only highlight the overall training pipeline for easy understanding, and we will also address some of the reviewers' questions during the experiment section. We'll only cover the parts of the experimental results presented in the paper. So here, let's go to the introduction. So anomaly detection is a fundamental task in many domains. Referring to many current detector methods, a prevailing assumption is that the training data provides a complete description of the normal class. On the contrary, normal data in real-world scenario is often incomplete or mildly contaminated. As a result, not every data point contributes positively to anomaly detection. Some even degrade the generalization by forcing the model to fit overly complex boundaries. Recent studies like data diet and dataset pruning have shown that discarding from 25% to 50% of the training data can maintain or even improve generalization. However, these methods mostly rely on the non-convex deep neural networks, which lack theoretical guarantees and are harder to interpret. So here comes the motivation of our research. Select a small but informative subset of normal data in a theoretically grounded way. We propose reinforcement learning OCSVM by combining IL with the geometric intuition of the one-class SVM. Before explaining our method, let me briefly introduce 2 related concepts in our paper. Firstly is reinforcement learning. Has been widely used in feature selection. It trains agent to adaptively pick informative subsets for better task performance. We adapt this idea to reformulate support vector selection in OCSVM as a MDP problem. Secondly is OCSVM. So the support vectors here are the key samples that lies on the decision boundary. Reinforcement learning trained agent aims to automatically identify these boundary points, which marked blue in the figures. And here we go to the methodology part. Based on the equation, for the dual problem of the OCSVM, we will got the training normal set can be divided into 2 categories. The non-support vectors lie outside the decision boundary, and the supporter vectors, which is the main points of our paper, will have a non-zero alpha weights, and for such kind of vectors, the bias rho can be calculated in this function. So with this foundation, we can set our goal to find SV by the kernel approximation with reinforcement learning subset selection. Assume we have a normal training set. The samples are mapped into high-dimensional feature space through the kernel track. The following pipeline is to learn the anomaly schooling functional based on a support vector subset S. with the size of the S defined as a hyperparameter M here, adaptively selected by a reinforcement learning agent. During the training, the agent observes the state of the current subset represented by its mean variance and how many samples have been selected, and then chooses a next sample according to an epsilon graded policy. The process continuously until the subset is full. At that point, we compute a sparse reward based on the final performance metrics to guide the agent to training. The process continuously the parameter updates the process following the standard DQN framework without any modification to its structure. For the reward part, we first inject a small number of the abnormal samples to form a validation set, which serves as the environment for DQN agent. The agent subset is then used to reconstruct the OCSVM decision boundary by recovering the weights and the offset with respect to this environment. When the subset becomes full, the episode terminates and the reward is calculated. Finally, the model evaluates its performance on the validation set using a matrix such as AUPRC, and this validation score is used as the reinforcement reward signal for the reinforcement learning agent. Here comes to the experiment part. We use two evaluation metrics in this paper, the AUPRC and AUROC. We train the model by setting one class as the positive class, while selecting the datasets originally designed for binaural or multi-class classification. This allows us to simultaneously evaluate the model's stability under heterogeneous anomaly distribution. So here comes the dataset and the parameter settings. For the D is the dimension of the dataset. This contains the trained normal dataset. The validation dataset contains the same data from the training dataset, and we inject several abnormal data to form the validation sets. And here is the test set which we never use in the training process. Here comes the results of the baseline. This slide summarizes the comparison with the baseline method across 6 benchmark datasets. We report both AUC-PR and AUC-ROC under two settings, mixed imbalanced on the left and unseen imbalanced dataset on the right. Overall, our proposed method achieves the best performance across most datasets. However, the baseline models each perform well on certain specific dataset. We further investigate the hyperparameter of the subset size M across different datasets. The results reveal that performance does not monotonically increase with larger M. Instead of a moderate number of supports often achieves better results. We specifically note the SONA dataset here. For the traditional SVM, performs poorly regardless of the hyperparameter settings. Roughly 50% of the training ports become the support vectors indicates that even after mapping to the kernel space, the decision boundary passes through a region with substantial data overlap and ambiguous normal samples. This almost everything is a support vector symptom, forces a complicated margin and a weak generalization. But in our SVM selection policy, we prompt parts of the contradictory normal samples so that we can get a tighter decision boundary to improve the final results. And here is a reviewer question for why we use sparse reward instead of the sparse reward instead of the dense reward. We use a terminal only sparse reward because it directly reflects the final subset quality, avoids stepwise noise, and making training more stable. And also, we conduct experiment later to compare the sparse reward and the dense reward. So the experiment results shows for the sparse reward, it's perform better on all datasets. Here is a visualization clearly shows that the reinforcement learning-based subset selection removes the redundant samples within dense clusters. You can see the reinforcement learning OCSVM selected a subset still preserving the overall structure distribution of the data. In contrast to the full data OCSVM, which tends to include many overlapping support vectors inside of the homogeneous regions. Our methods focuses on the boundary representative samples that maintain cluster topology but simplify the decision surface. This leads to a more compact model that generalizes better cross-on-seed data. Here comes the conclusion. So in this work, we introduced a reinforcement learning-based subset selection framework to regularize OCSVM for imbalanced anomaly detection. By reformulating the support vector selection as a sequential decision problem, the method learns to identify compact and representative subsets that align directly with evaluation metrics. Experimental results confirm that the approach consistently outperforms traditional OCSVM and deep neural network models and large language models, especially under the unseen imbalanced scenarios. So for the further direction, we will do more experiment on the explainability by comparing the reinforcement learning selected supports with the original OCSVM supports. Thank you for your attention. That's all for the presentation. Let me know if you have any questions. And